Hello, and welcome back. Today, I want to start talking about switch mode power supply topologies by first looking at how these circuits can be classified. I do not want to make an exhaustive list of all of the topologies, but rather look at what are the various features that can be achieved, and how this will split the multiple topologies into categories. So, the first thing to look at is the relationship between the input and the output voltage of the power supply. Now, unlike a linear power supply where the output always is smaller than the input voltage, with a switching supply, we can have some other types as well. So, starting off with something similar to the linear power supply, we have topologies where the output is always smaller than the input, but of the same polarity. So in this category, also known as step-down converters, we have things like the buck converter. Now, on the other hand, if we need higher voltages, so higher output than input voltages, we have the step-up converter category, with the main representative being the boost converter. Now, other than these two, we also have a very important category with converters where the output can either be higher or lower than the input voltage. So which regime you're in depends on the exact duty cycle. No other change needs to be done to the converter. And well, in this category, we have things like the SEPIC converter. Finally, it's important to consider inverting converters. So topologies where the output is of a different polarity compared to the input. Commonly, the input will be a positive and the output a negative voltage. This sort of behavior can be achieved with the buck-boost converter. Another important classification sees converters split based on the electrical link between the input and the output. So if there is or if there isn't a link. So here we have the non-isolated converters, so all of the previous ones that we've looked at. These have a direct connection between the input and output, usually through the ground line. Now, the alternative to this is to have isolated converters. Here, there is no galvanic connection between the two sides. In this category, you will find most transformer-based converters, one specific example being the flyback converter. Now, it's important to observe that since a transformer and complete separation is used, you can make the output of either larger, smaller, or even inverted value compared to the input. With isolating transformers, there is no dedicated topology based on the input to output voltage relationship anymore, since the main thing that decides the voltage ratio will be the turns ratio and the exact ground connection on the secondary side. Isolation usually comes with more expensive components. The transformer is more expensive than a basic inductor, but in certain cases, such a topology will be mandatory for safety reasons. In general, all of the devices plugged into the mains have some sort of isolation topology in use to protect the end user from accidental electric shocks. Next classification refers to the switching element. So any switching converter has at least one active switching element in the form of a transistor. The important thing that can be made different here is the way in which the switch transitions from the on to the off state and vice versa. So converters can be split into soft and hard switching. So hard switching means that both the voltage and the current running through your switching element will suddenly change at the moment of switching, whereas soft switching refers to keeping either the voltage or the current at a zero value during the exact transition, thus greatly reducing switching losses. So in the soft switching category, we can have special control schemes that keep the converter in some form of boundary conduction mode, so this can be applied to almost all topologies. In this example, both waveforms can be applied to the generic buck converter, with the main difference that on the right side, with soft switching, we have zero current switching during the turning on phase, but you also have dedicated resonant topologies where the power stage is driven with a switching frequency equal to its self-resonance. An example of this being the LLC converter. Last important classification refers to the energy storage mode. What kind of component do you use to store the energy that is being switched? So here we have two main categories: magnetic field storage using inductors or transformers, and electric field storage using capacitors. And while a third bonus category that includes both. So magnetic field storage is used in most topologies you already associate with switch mode power supplies, like the buck or the flyback converter. But as an alternative, you also have capacitive or electric field storage, where most charge pump type of circuits fit in. Now, in general, a charge pump based circuit is much cheaper, so capacitors will be cheaper than inductors, but this type of circuit does not allow the generation of an arbitrary output voltage. Only specific input to output voltage ratios are possible. Now, other than these two, you can create a third category for power supplies that have both storage elements. So something like the Chook converter. This uses both inductors to store the energy as well as capacitors. But it's important to notice that the more storage elements you have, the higher the overall losses will be, since each element will be losing a bit of energy. Before moving on, we shortly need to mention a variation that can be applied to most topologies, which concerns the passive switch. So, in all converter topologies, other than the active switch, the transistor, you have an extra passive switch, usually in the form of a diode. This component still acts like a switch, but it will transition automatically based on the voltages present on its terminals. So the change that can be done with the basic converter is to replace the diode with another transistor, which is driven in phase opposition to the first one. This classification therefore splits converters into non-synchronous and synchronous converters. Now, the main reason to do this is to reduce power dissipation, since during conduction, the voltage drop on the diode will be larger than the voltage drop that can occur on a transistor, and therefore the power dissipation will also be larger on the diode compared to the transistor. So the synchronous type of converter can be made much more efficient than the non-synchronous type. Now, once you're familiar with the basic single output topologies, you can start complicating things by combining multiple pieces of the same or combining different topologies to get various benefits and headaches. First thing to mention is multiphasing. So usually when large currents are involved, it's helpful to put multiple converters in parallel. Now, this is not always the best idea, since if you have individual control circuits, they will give slightly different output voltages, and then you won't really have equal currents running through your parallel converters. Now, the special thing about multiphasing is that you have a single control circuit that drives all of the switches in a synchronized fashion, but out of phase. The exact phase is usually 360 degrees divided by the number of parallel supplies. So if you just put simple supplies in parallel, the circuits will be running at uncontrolled phase shifts, which will not really stay a constant. So the main advantage of multiphasing is the way in which current is being drawn from the input side and delivered to the output. By controlling the phase, you get a more uniform energy draw and a more uniform energy delivery. So smaller capacitors can be used than if you would have a large single phase converter of the equivalent power. This technique is commonly used in supplying high current loads like computer CPUs and GPUs. Now, another variation relies on combining different base topologies to get the benefits from the individual types. Some examples here are the 4-switch buck-boost converter, basically a buck converter interconnected with a boost converter. So this works like a non-inverting buck or boost, depending on which set of switches is being used. Another example is the boost charge pump topology, which allows the possibility to get higher voltage ratios without really compromising the duty cycle. So this is built around a basic boost stage with a charge pump put on top. And the last example to mention today is the boost flyback converter, basically a boost converter with a flyback added on top. So this allows the usage of coupled inductors to get large output voltage ratios. Now, in general, the possibilities of combining different switching topologies are quite endless, but some combinations will provide benefits, while others not really. Now, all of the previous categories had a single output voltage, but that does not have to be the case. So the next thing to observe is supply combinations that generate multiple output voltages. So one common example is something like a computer's power supply. A single push-pull driving stage that drives a transformer, which has multiple secondary windings for the various voltages that are needed in the system. Now, in general, with transformer-based topologies, multiple secondaries can be added for whatever voltage is needed. Another example can be built around the basic boost converter, so other than the base boost output voltage, you can also add a charge pump stage on top of it to get a higher voltage, but you can also add an inverting charge pump stage to also get a negative voltage. So around the single switch, you can get 3 different voltages. The main issue with any single converter with multiple outputs is the limited control that you have. You can only precisely regulate one output. All of the other ones can be monitored, but as is, the converter cannot adjust each output independently. So the way in which you would fix this, when you actually need it, is to add an extra voltage regulator on each of the unregulated lines. So one line will be kept in regulation by the control circuit, but every other line does need something else. Now, this specific regulator can be as simple as a basic linear regulator or a more complex and expensive switching regulator. However, the most interesting solution that I found to this problem is the magnetic amplifier-based regulator, which simply put is a linear regulator for AC currents, and it uses a saturable inductor. It's more efficient than the linear regulator, but it's also more simple than the switching regulator. However, it's quite obsolete by today's standards. In the end, it's important to understand just how vast the field of power electronics is. Based on your exact use case, multiple power topologies will work, but the difficulty relies in determining which topology offers the best compromise between price and performance for your particular use case. And with that said, hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.